Hey guys, and welcome back to part 2 of coding Tetris in Python with Pygame. So let's get right into it. In this video, we're going to be finishing a few other functions. We're going to be doing valid space, convert shape format. We're going to be coding a bit in the main, and we're also just going to be fixing a small mistake I made in the last video. So this code right here in draw grid, yes, this does draw our grid, but this is not what I intended this function to do, and I kind of just realized this when I was looking over the video and looking over the code. So we're just going to copy this code from draw grid, okay, delete it out of there, and we're just going to paste it down here at the bottom of draw window, okay? So now we just have this after we're blending the label, we have whatever code we had within draw grid, okay? Because draw grid, what this actually was supposed to do is draw the lines for the grid. So I kind of got this mixed up while I was going through the tutorial. So we're going to finish draw grid now, and what this is going to do is going to draw those gray lines over top of all of our different colors so that we can kind of see where each block is and we can see the actual grid structure. So let's get started with this. Say SX, which stands for start X, is equal to top left X, okay, and then SY is equal to top left Y, like that. All right, and this is just so I don't have to keep typing top left X, top left Y. It just makes it a little bit shorter for us. Okay, now I'm just going to say, I'm going to set up a for loop. I'm going to say for I in range, and this is going to be the length of the grid, so how many rows we have. And say for J in range, and this one is now going to be the len of grid I, so how many columns in each row. And then here we're going to be drawing lines. Okay, so for every row, we're going to draw a line. So pygame.draw.line. We need a surface. Let's give it a surface. We need a color. In this case, it's going to be gray. So gray color code standard is 128, 128, 128. And then we need two positions, okay? So the start position is going to be equal to SX, all right? And then SY plus, I believe, multiplied by block size. And I think that is actually correct. Okay, now for the end position, well, it's going to be the same X value because we're just drawing, or actually it's going to be, let me just check here. Yeah, it's going to be a X value that is just equal to the width. So SX plus whatever the play width is. And then the Y value is going to be the same here because if you think about it, we're going to be at the same Y value each time. We're drawing a horizontal line. Every horizontal line is going to have the same two Y values, and the X value is just going to be changed. Okay, so I'm just going to copy this and paste it in here now. Okay, all right, I don't know why that did that, but we'll just go back like that. Okay, so now what we're going to do is we're just going to do this. Okay, so SX plus J multiplied by block size. Okay, SY can actually just stay like this. Okay, and then for SX, same thing, we're going to SX plus J multiplied by block size, and J is again as our current column, and then this one SY plus play underscore, oops, we need a plus sign here, plus play underscore height, like that. Okay, and that should be drawing us 20 vertical lines and then 10 horizontal lines down the screen, giving us a grid. And kind of the way that works is every time we loop through a new row, we're simply changing the Y value of what line we're drawing, and then these X values are going to stay static just at the left side and the right side of the screen. And then the way that we do it here is we have the X values that constantly are changing every column, and then the Y values are staying static, being the top of the screen and the bottom of the screen to draw the vertical lines. And that's what I wanted to do within this draw grid function. So now that's all kind of sorted out, and we fixed like a small mistake. Don't get me wrong, you can still have that other code up here, like it still works fine, but just in terms of what I actually wanted to do with these functions, that's the way we needed to fix it. Okay, so now that we've done that, what I want to start doing is getting into this convert shape format. Okay, now this is probably the most complicated function, I want to say, within our program, and what this is going to take as an argument or a parameter is just the shape. Now this is what I was talking about before. So when we have a shape, it looks something like this, right? So we have zeros and we have periods. Now this looks nice to us, like we can tell what kind of shape this is, but the computer has no idea. So how can we get this into a form that the computer can read? And ideally we want it to give us positions within the grid of where blocks exist. And then we're not going to give position if the block doesn't exist. So if there's a period like this, okay? And you'll see what I mean as we start coding this function. And that's what the goal of this function is to do, to take that information and put it into something that's actually useful to us. So we want a bunch of positions. That's the goal. From these like lists, we want to generate a list of positions, and then based on those positions, we can do things. We can check them, we can draw them, and so on. So I'm just going to create a list called format. Don't worry if it's a keyword, it'll just override it. We're going to say when we're given a shape, we're actually given a piece object. So I don't know why I'm calling it shape, but whatever, that's fine. So shape.shape, and then we can just do is equal to, and I'll talk about this in a second, shape.rotation modulus the length of shape.shape. Okay, so what this does is actually gives us the sublist that we need. So this needs to be spelled correctly. Don't know how I butchered that so bad. Okay, shape.shape. So if we look again here, whenever we're past a shape, we're actually past something like this, right? So we're past the shape object and its shape property. So right here looks something like this. Looks like the variable t, which would have a list full of lists. So we want to get the actual sublist. So which one? This list, right? That's the one we want. So the way we do that is by getting the shape rotation modulus the length of the shape. So for example, if our current rotation is 0, like we haven't rotated yet, then what's going to happen is we're going to have 0 modulus the length of shape. In this case, the length would be 4, so we get 0. So we're given this first shape. Now if we have 1, we're given this. If we have 2, we're given this. If we have 3, we're given this. And if we have 4, then we go back and we get this one, okay? And it just keeps going and keeps going because modulus simply just gives us the remainder. So that's how we can tell what the actual current shape is within that main list, okay? Hope that makes sense. So now that we've done that, what we want to do is we want to set up a loop. And because we want to look through every row and every column, and then based on if there's a 0 or a period, we're going to do something. So we're going to say for I, comma, and because we want the line as well, in enumerate, right? And then format, okay? Because format is the list that contains like the actual 0s and 1s, okay? We're just going to say row is equal to list of line. This just gives us a nice list format that we can deal with, making it easier for us. I'm going to say for j in, or j, comma, column, sorry, in enumerate, and now row. So now every row we're getting the current line, and then we're going to loop through the line and look for either a 0 or a period. So we're going to say if column, which is going to be, for example, if we have something like this, it's going to look like 0, 0. Okay, so this is what our row is going to look like. So when we start looping, j will be 0 and column will be a period, okay? Just in case you're kind of confused there. Okay, so for if column equals, and it's going to be string 0, then we know that we've hit like a position, like this cube exists here. So what we want to do is we want to add the position to our positions list. Now it's not so simple as just to add the current I and j value. We actually have to add something else, and I'll show you right now. I'm just going to type it out and then kind of talk about it, okay? So shape.x plus j, and then shape.y plus I, okay? So this is our x value. It's the current value of the shape, because if the shape is already moving down the screen or just moving left and right, well, we need to add that to whatever the j value is, so whatever column we're in within this list, okay? And then same thing with the y value, so whatever the current y value is of our shape, we're going to add whatever column or whatever row, sorry, we're now in as for the y value, okay? And that is the positions that we need in these positions list. Okay, so now that we've done that, we just have to modify these positions slightly. We just have to give them an offset, okay? And I'll talk about why why we have to do this. So for I pause in enumerate positions, okay? Then we're going to say positions I is equal to, and then this is going to be the current position, okay? So we just need to put this in a tuple because that's the way we're going to give it. Pause 0, -2, and pause 1, -4. Okay, so now let's break this down and kind of talk about exactly what's going on. So we start off blank list positions. We're just getting the actual shape within this list. So for example, we would get something like this, okay? And then we're looping through it, and where am I? Sorry. And we're pretty much just checking if a 0 exists in each position of that shape, okay? If that exists, then we're going to add that position into our list. And the way we do that is simply by getting the x plus whatever the current column is that we're looping through, and whatever the current row is plus y, okay? Now that we've got that, the issue is that if we look here, we're going to get something like, for a position list here, we'll get something like 3, 1, and then we'll get 3, 2, we'll get 3, 3, and we'll get 3, 4, okay? Now the issue with that is we're adding the current x value plus these 2 periods and the O. So we need to remove these kind of trailing periods, right? Because that's going to result in our positions being all offsetted to the right by too much. Same thing with these y values, okay? Because when we're counting this row, we're saying, well, this is 1 lower than this row. So our current y value, say it was 0, and we're adding to it. Now instead of just adding 1, we're going to be adding 2. So everything's going to be offset down. So the way that we can kind of fix this is just by offsetting by a constant. And by offsetting, I'm just going to take every x value that we've added and subtract 2 from it, and every y value that we've added and subtract 4 from it. Now what this is going to do is simply just move everything to the left and up, so that when we are displaying it, it's just more accurate to the screen, okay? You guys can see what's going to happen if you don't offset this, and you'll notice that you kind of run into a few errors. So just run with me on this, right? And just kind of, you should see how this works later on, okay? Okay, so now that we've converted the shape format, I want to go and code valid space now, okay? So valid space is going to take 2 parameters, shape and grid, all right? And we're going to check the grid to see if we're moving into a valid space. So what I'm going to do here is I'm going to create 2 lists. Okay, I'm going to say accepted. How do you spell accepted? Accepted underscore pause. So these are just going to be the positions that are actually valid, okay, is equal to, and just flow with me on this, I'll talk about it in a second, for ji, and then within this list for j in range 10. This is similar to what we did in the last tutorial, and then for I in range 20. Okay, so this is really similar to the way that we created the grid. We're just getting every single possible position for a 10 by 20 grid, okay, and we're just adding it in a tuple in accepted positions. Okay, that's great, but the thing is, I want to convert this into a one-dimensional list. So this is the way that we can do this and make all the positions, but now how do we flatten this list? So this is actually how you do this, okay? So accepted pause is going to be equal to, and this is one way, there's many, j for sub in accepted positions, and then one more for j in sub, okay? So what this is actually doing now is it's pretty much taking all the positions in our list and just adding it into a one-dimensional list. And then we're just overriding this list with that. So see if you guys can understand that. If not, don't worry about it. Just know that all this does is simply flatten this list. So we go from looking something like this, what do you call it, like 0, 1, and then having another list, embedded. I'm just trying to show an example here, 2, 3. So we go from that to something that kind of looks like this, and we just have the positions in it now, so we don't have those sub lists, and this just makes it a lot easier to loop through. Okay, so now we just have 0, 1, 2, 3 rather than having these embedded lists full of other tuples. Okay, that's all we're doing with this line. Okay, so after we do that, what we want to do is we want to get all these positions, or we're going to get the shape and we're going to convert it into our positions, right? Because remember, whenever we get a shape, it looks something like this. It means nothing to us. We need to first convert it into positions before we can compare it against other positions in our grid. So we're going to use this convert shape format grid, our convert shape format. We're going to pass it the shape, and we're just going to store this in a variable, and I guess we're going to call it, what should we call it? Formatted, okay? Because I guess that makes sense. We formatted our shape, so now we can use this and kind of compare it against accepted positions. So here we're going to have a list that looks like something with a bunch of positions in it, and then this one we're going to have a list that has a bunch of positions in it. So you might see where we're going here in terms of how to compare these things. Okay, so now that we've done that, we've kind of got all our data ready to check. This is the really easy part. So we're just going to say for position in formatted, and all we're going to do now is just check if this position exists within accepted positions, because accepted position is every position that we're allowed to have, right? So we're going to say if pause not in accepted position, and this is an important part, pause 1 is greater than -1, return false, and then otherwise, so if we make it through that loop, that means we had all our positions accepted, we can return true. Okay, so let's talk about this really quickly. The reason I have this if pause 1, so the y value is greater than -1, is because when we give this offset of 4, what ends up happening is we get some, when we spawn in our shapes, they're going to spawn above the screen. Now we actually want this because we don't want our shape to show up on the screen. We want it to start falling before it's actually seen. So typically this means a Y position is going to start at like -1 or -2. So the thing is, while it's falling, we're checking if it's in a valid position, right? But the thing is, it's not going to be in a valid position if it's negative. So we just want to make sure that we're only asking if it's in a valid position if the Y value is greater than -1, so greater than or equal to 0, okay? And this is just a really easy way to tell us, well, are we on the grid or not? So let's give an example. Say we're trying to move left and we're already at the edge of the screen. So that means we're going to have an X value of -1. Well, that position of -1, whatever Y value, is not going to be in this accepted position list. So when we try this, we're going to return false, and it's not going to allow us to move left. And that is the whole point of that. And now, okay. What am I doing here? Okay, so I also just want to modify this part up here. So I have for j, I in range, for j in range, if I in range 20, I want to just change something here. Okay, so what I'm going to do actually is I'm going to say if grid I, j equals, and then the color 0, 0, 0. Okay, so this is an important part. I was kind of waiting. I was kind of thinking about this. So pretty much we're only going to add this position into our accepted position if it's empty, which actually makes a lot of sense. Because think about it, if we already have a color in that position, then that's not a valid position. We can't move into where a piece already exists. So what this condition does is it says, okay, well, we're only adding this position now if this is true. So if ij is true, then we're good. We can add the position. If it's not 0, 0, 0, that means something exists in there. So that's why we're not going to add it into our accepted positions. Okay, so I know this looks kind of confusing because I'm doing like a bunch of embedded for loops. This just saves us a few lines. And it's kind of a cool way to create a list in one liner. It's like the Python-y way. So I figured I'd do that for most of the stuff in here. Okay, so now that we've done that, what else can we code? Well, you know what? While we're here, we can code check lost, all right? This one's a really easy function. This is just simply going to check if any of the positions are, above the screen. So if we hit Y value of 0, then we know that we're above the screen and we've actually lost. So the way to do this, we're going to say for pause in positions, because what this is going to do is we're going to pass a list of positions. So we're going to get every pause now in the position. We're going to say xy is equal to pause, which is simply just splitting up the tuple because we know we're going to get something that looks in the form of like 3, 4. Okay, and we're going to say if y is less than 1, so equal to 0 or greater, then return true, else, or we don't even need an else, let's say return false down here. So if every position is less than or greater than y, or whatever, 1, then we will return false because we haven't lost yet. Otherwise, we're returning true. Okay, so we're almost getting there. Now I want to go down to the main, and I want to finish coding up some stuff in here. So last time we kind of just left it at this, like moving pieces around, whatever. But we have these variables, okay? So change piece, next piece, clock, fall time that we're not using. So what I'm going to do now is I'm going to show you guys how we can actually move our shape down our screen at like a regular time interval. So I'm going to create a variable here actually called false speed. And this is how long it's going to take before each shape starts falling, okay? So we'll talk about how to do this. I'm going to start coding it now. So pretty much we're going to say up here, and I didn't do this before, but just follow along, grid equals create grid based on locked positions. The reason we're doing this, I know we already created grid up here, is because every time that we move, we have a chance to be adding something to locked positions. We're going to do that later. Because, for example, if we hit the bottom of the screen, well, now locked position is going to be equal to something else because it's going to have a new shape in it. So we need to constantly update the grid so that when we're drawing it to the screen, we get like an updated version. So that's why I'm doing that up here, okay? I also need to, actually, I don't think I need to do that here. We need to add to fall time, okay? So the way we're going to add to fall time, because this is going to track, how long since like the last loop ran, is by using this clock object that I set up here, okay? So before I add to that, after here, I'm going to do clock.tick, and then I'm going to add this, and I'll talk about this after I do it. So clock.get underscore raw time, like that, okay? So the way that this works is this raw time actually gets the amount of time since this last clock.tick. So when I first add, it's going to be 0 because we haven't yet ticked the clock. And the next iteration, it's going to see how long it took this while loop to run. And then it's going to simply add that amount, okay? So it's actually going to give us real time. This means that this should technically run at the exact same speed on everyone's computer and everyone's machine. Because I know when I use FPS, FPS is dependent on kind of the speed of, what do you call it, your actual computer sometimes, like the way I did it in other games. So this is a better way to do it. So now what I'm going to do is, since I've now incremented the fall time, and this is going to be given to us in milliseconds, so like 1 second would be 1,000, that's that number, and our fall speed is in, well, 0.27. So what I need to do is I have to say if fall time divided by 1,000 is greater than fall speed, then what we're going to do is we're going to reset fall time equal to 0, and we're going to add 1 to the current y value. So, which means we're moving down the piece 1. So this is going to automatically now move our piece down. Now the thing is, what if our piece will hit the bottom of the screen, or what if it's moving into a position we can't move into? So this is the same thing we've kind of done in here. What we're going to do is we're going to say again, if not valid position or valid space, whatever, given the current piece and our grid, I believe at least grid, okay, then, and actually we're going to check one other condition, and our current piece dot y is greater than 0. So this means that we're not at like the top of the screen, because the same thing with negative values, all right, is greater than 0. Then what we're going to do is we're going to subtract 1 from the current piece. So y minus equal 1, because that means, well, we moved into an invalid position. So let's move back up 1 and pretend like that never happened. And we're just going to say change piece is equal to true. Now the reason I'm setting change piece equal to true, because think about it, right? If we're moving down, and we move into a position that's not valid, well, we know we didn't move left or right off the screen because we were moving down. That means we must have either hit the bottom of the screen or hit another piece. So in that instance, we need to stop moving this piece and we need to change it. And what changing piece is going to do, we're going to do that later, is simply going to lock all the positions, what they're currently in, and then it's going to make this next piece generate down the screen. And I'll show you that in a second, but this is kind of the way to check it, and it's the easier way. Then you don't have to check like the y values and all that stuff, okay? All right, so now that we've done that, let's move down here to the bottom of main, and let's start adding a few things. Okay, so what I want to do down here, I want to say shape positions, so shape underscore pause, is equal to convert shape format current piece. Because what we're going to do now is we're going to check all the positions of the piece moving down to see if, well, we've hit the ground, or to see if we need to lock it, okay? So, and we're going to add all that color to the grid so that when we're drawing it, we actually see the piece. Because right now, we have the piece, but we don't add its color into the grid, so we're not actually going to see it show up. So we first need to add it to the grid so we can draw it and we can see it moving. So to do that, we're going to say for I in range, the len of shape positions, okay? What we're going to do here is going to say x, y equals shape positions of I, because that's the current iteration, the current one we're looking through. We're going to say if y is greater than -1, so this means that we're not above the screen. Then we say grid y x equals current piece dot color, okay? Because remember, the grid stores a bunch of different colors, so all we're doing in the grid is giving different colors, and based on that position in the grid, so yx, which is going to be this shape, all the shape positions, we're going to draw that color. Now the reason again I have this -1 is because imagine that we're at the top of the screen and we try to draw it, or we're above the screen. We have a position with a -y value. So if we throw -1, we're not actually going to get an error in grid here, but it's going to end up looking like it's at the bottom of the screen and then moving to the top, and it's just going to look weird. If you guys want to see what it looks like without this, just remove this condition and you'll see that why I have it added in. Okay, so now what we're going to do is we're going to check this change piece variable. So I put it up here, change piece. This means that we've hit the bottom or we've hit something. What we're going to do now is we're going to update locked positions. And this is when I'm going to start talking about locked positions, okay? So for pause, actually, in shape positions. All right, we're going to say P is equal to pause 0, pause 1. All right, I don't know why I do this, but I think there's a reason for it, so let's just run with it. And we're going to say locked positions P is equal to current piece dot color. Okay, so what is this? Well, locked positions is going to be a dictionary in a form like this, all right? It's going to have a tuple in here. It's going to have a position, so like 1, 2, colon, and then we're going to have a color, and the color is going to be another tuple, but RGB values, okay? So for example, 255.00. The reason we have this is so that when we pass locked positions into our grid like this, all right, we can get each of those positions in the grid and then update the color of grid. So every time that we have like a locked position, and a locked position, it simply means our piece is no longer moving, it's hit the bottom of the screen and we're onto a new piece, we can get the position and we can get the color, and then we can update the grid based on that, and we can keep that in there, okay? And that's the way that locked position works. So it's a dictionary with the key of a position and the value of a color. All right, that's kind of like the data structure for that. Now what we're going to do after this, after we update our locked positions and we add positions to it, we're going to say current piece equals next piece. Okay, so we're just going to change that. And now since we've said current piece is now equal to next piece, well, we need to update next piece. So let's get a new shape because we're just moving forward with the game. And now, of course, we got to say change piece equals false because we're on to a new piece that's going to spawn at the top of the screen. Okay, and I think that is about it. What we also want to do actually is we're going to check if we lost the game, and I think I do this after draw window. I don't think it really matters, but we're just going to say if check lost based on, what do you call it, locked positions. Okay, so these are all the positions of the shapes. Then we're just going to say run is equal to false, and that's going to break us out of this while loop. And you know what, while we're here, let's indent out and let's just go Pygame dot, what is it? I think it's .display.quit or something. Yeah, .display.quit. So we're actually just exiting out of our game. Okay, so I've done a lot here. I think I'm going to stop it here. And in the next video, we're going to get into kind of doing clearing the rows, which is also very complicated. And I think we're going to test this a few times, go through, probably fix a few bugs. And yeah, so that's been it for this video. If you guys enjoyed, please make sure you leave a like and subscribe, and I will see you again in the next one.